Hello and welcome to this next session on instrumental analytical chemistry, where we continue on our journey to understand certain aspects of absorption, molecular spectroscopy, and in this case, today, other kinds of absorption spectroscopy in the form of atomic spectroscopy, where we'll be having an overview of AAS, which is atomic absorption spectroscopy. Atomic absorption spectroscopy is one of the premier ways in which we can detect specific elements in our environmental samples, as well as particular elements in our industrial samples that we have produced. It is a very powerful technique. However, it must be taken with the caveat that unfortunately the sample will be destroyed through the analysis process. So this is not for very small amounts of sample. This is really for a bulk process. So atomic spectroscopy can be broadly broken down into four major categories. So there is atomic absorption spectroscopy, AAS. There is atomic emission spectroscopy, that's AES. Atomic fluorescence spectroscopy, that's AFS. Mass to charge, that's ICP-MS. And there are specialist journals associated with this. So the Journal of Analytical Atomic Spectrometry is specifically dealing with atomic spectroscopy studies. So what we have here is the three or four major types here. They're all basically doing similar things. They're taking our sample, and what they're doing with that sample is that they are combusting it in some way. Now, the differences are either what they are detecting after combustion is complete or how they are combusting. So the first three here are pretty similar in terms of the internal workings of the machine. They're the traditional forms. What they are measuring, though, is different. In AAS, it is analogous to the UV-Vis spectroscopy that we have dealt with before. Here, though, instead of it being the molecule that is absorbing, it is an atom. So in this sense, this is an alternative form of absorption spectroscopy focused on particular atoms. Now, the reason why it's kind of useful is because it can give us all of a particular atom and all of the absorption of that particular atom in a sample. So it's not just going to be like one molecule that's absorbing or something like that. It can be the entire carbon in one sample, the entire iron in one sample, that kind of thing. Atomic emission spectroscopy then is related with the emission of the sample after it has absorbed something. Atomic fluorescence spectroscopy is then dealing with the fluorescence which comes from an excited sample which has been atomized using our atomic fluorescence spectroscopy instrument. And then mass to charge, that's ICP-MS. That is possibly the more modern version. It uses something called inductively coupled plasma, which is a very, very high temperature flame source, much higher than the others. And this intense light source is capable of allowing us to measure those intransigent materials which just don't really want to burn. And so it's coupled usually with a mass spectroscopy so that we can do two measurements at once. And so that's really a very nice development in this area. So an overview. So generally, as I've said, there's the three processes. There is the atomic absorption spectroscopy, atomic emission spectroscopy, and atomic fluorescence spectroscopy. So fluorescence is sort of stimulated emission. Emission is just, well, emission. And fluorescence absorption, or sorry, atomic absorption is whenever it absorbs the light in a manner which is very similar to our UV-Vis spectroscopy. So this is sort of like an overview of the three. So we have here our flame, which is where our sample is going to be pumped into. So we have this flame. There are various different types of fuel sources. We'll talk about those later. But in the meantime, let's consider this flame as just being hot enough to burn whatever sample it is that we're passing through it. So our sample is usually drawn in via capillary action. So, and then atomized onto our flame such that the flame pulls the sample into it and it burns it. And so that change in pressure helps to pull our sample along the the tube into the flame. Usually, we're dealing with liquid samples, though samples that are gaseous and solid are theoretically possible. Solid samples are definitely pretty easy to do, although there are some caveats, and we'll consider that later on as we get through this section of the course. So the flame burns the sample, basically destroys any molecular bonds which are involved, atomizes it completely so that it's basically just whatever atom is in the flame, like whether it be carbon, whether it be hydrogen, whether it be oxygen, whether it be sodium, iron, whatever. It produces the atom. Then, depending on what it is that we want to measure, so for example, say we want to measure some iron in our sample, then if we want to measure it via emission, we don't need any light source emission, simply just measures any relaxation from the ground state, which is created by the heat of the flame. That energy from the flame can cause excitation to excited states. Then what we see is relaxations back down to the ground state. And then those atomic emission transitions can be picked up using can be discriminated using our monochromator, and then can be detected at specific wavelengths by our detector. So as I said, as we saw in previous sessions, this monochromator is very powerful, and we'll use it again here. So this is AES. Then if we want to deal with absorption measurements, of course, we need to be producing light of a particular wavelength. So we would use hollow cathode lamps in that case. So these hollow cathode lamps are, we've come across them in previous lectures, but we didn't really dwell on them very much. In this lecture, we're going to be, well, not this one, the next lecture, we're going to be dealing with them in considerable more detail. Basically, what they do is they produce light of a specific wavelength, which is specific exactly to the analyte element that we are interested in, such that it means that we only get absorption from the element of interest and we ignore the rest. This means that this is kind of one of the drawbacks, I guess, of this technique, in the sense that it can't really measure everything at once. You have to measure it one by one in your sample. That's not really a big deal if you're only interested in one thing, but if you're interested in knowing the composition of the sample, there may be other techniques which may be better. This is really for quantitative or analytical measurements, this AAS. So after the lamp has produced its electromagnetic radiation, which will pass through the flame, which will then be absorbed by the atomized elements. We will get the atomic absorption signal. We pass it through the monochromator again to discriminate it at the discriminate it for the detector, so we can get a specific wavelength. Then in fluorescence, we need some sort of laser source to produce light of a specific wavelength. And then we get the fluorescence, which is stimulated emission. So the fluorescence, so we have an absorption of light, and then this causes fluorescence to happen. And again, this fluorescent signal is picked up by the monochromator, and then it passes through the detector, and we have an AFS sample. And then we also have the fourth one, the mass to charge ICP-MS, which we will learn about later. It uses it's pretty similar to the process involved here. So it burns the sample, atomizes it, and then we measure it. So most compounds are atoms in the gas phase at high temperature, 2000 to 6000 Kelvin. So here is the flow of one of these spectrometers. So we have an AAS experiment. We have a hollow cathode lamp, which produces the light of incident in power, which is P0, which passes through the flame. And then any sample which is in the flame that has been burnt will absorb if it is the right wavelength. And then we'll get the power after absorption events. They'll pass it through the monochromator and then go to the detector and be amplified for electronically. And then we will get a readout on the computer as to how much or what the signal is. And then we can use our calibration curves to determine the quantities involved. So here we have our analyte sample in the beaker. So the flow of the air and the fuel passes through this instrument, and it gathers up through capillary action the sample. So what we have here is air, fuel, and the sample. It mixes together in the flame, and everything gets burnt. So the air here can also be changed to like oxygen or more combustible materials. Fuel, usually things like acetylene gas, so that we can reach those really high temperatures. So the flame in the atomic spectroscopy is similar to the cuvette in molecular spectroscopy in the UV-Vis spectroscopy that we talked about earlier, and we will continue to talk about as we go through this course. So the path length in the flame as well. So this AAS experiment uses the same Beer-Lambert law as we did for the molecular spectroscopy. So we need a path length. So it's basically the length of the flame, in this case, about 10 centimeters. An AFS experiment then. So here is an example of an AFS experiment. So what we're doing is we're getting the atomic fluorescence from lead at 405.8 nanometers. And so we have an atomization process, which is incident on our sample, which is a 6 nanosecond pulse of 10,064 nanometer laser radiation. So here we have a capillary tube, we have our liquid drop, we have our laser for vaporization. So in this sense, we're not using a flame anymore, but what we're doing is we're vaporizing using a high-powered laser. Then we're using a different laser for excitation. So once the sample has been atomized, we use this other laser, it's 193 nanometer laser, for excitation of the atomized sample or the vaporized sample. And then from that excitation laser, we will get some atomic fluorescence, and that will be detected, in this case, at 405.8 nanometers. And then we have here a bunch of standards which have their signals. So 0 PPS, ppb, 5 ppb, and so on. We see this peak, which corresponds to our lead. And so here's the signal from tap water containing 2 parts per billion lead. The AES experiment then, so we're looking at a bandwidth of radiation absorbed or emitted. Molecular spectroscopy gives us around about 100 nanometers resolution, whereas atomic spectroscopy gives us around about 0.001 nanometers. So we have very sharp line spectra, so there's little overlap between the spectral elements, and we can measure multiple elements simultaneously, around about 70 different elements. Depends on the instrument, really. But yeah, around about 70. So this is only possible for the emission spectroscopy because it doesn't use a light source. So what's happening is we're just getting the emission from whatever is in the flame. So we're just looking at the flame, trying to remove any background caused by the light that comes from the flame. And then we get our atomic spectroscopy emission lines, which are seen here on the left for like iron, nickel, chromium sample. You can see here some of them are very close together, which is why it's important that we do have this very sharp line spectra, and so that we can properly resolve the peaks. We have very good resolution just atomically, and so it really comes down to the quality of your monochromator as to whether or not we can resolve these properly. So atomization, so flames, furnaces, and plasma. So atomizer converts a sample to an atomic vapor. So that's the point of it. So what it's doing is it's sort of like mixing all together our flame, our fuel, our air, and our sample, and then burning it. How the atomization happens depends on the particular technique that we're using. So we use flames for atomic absorption spectroscopy and atomic emission spectroscopy, and we're dealing with liquid samples in those cases usually. In the case of a furnace, we can do AAS and AES on liquids or solid samples. So a furnace is basically just a very, very hot oven. Plasma then, so that's going to be AES and ICP-MS, so that's going to be a liquid sample. And so the accuracy and precision of atomic spectroscopy is critically dependent on the atomization and sample introduction. So we have to be very, very particular and very, very careful about how we go about these measurements in order to make sure that we're not introducing any of our determinant errors or systematic errors, and so that we're avoiding as much as possible any interference from the user or the scientist, and that can help us to ensure that the value that we get out at the end is going to be meaningful. So here is a schematic of a burner, a flame. So what we have here is a sample and a nebulizer. So the nebulizer creates an aerosol from the liquid sample. So the liquid sample passes through, and then it gets nebulized as it goes through. So it produces like a kind of a fine mist. And then the glass bead is there to gather up any like large droplets. And so the aerosol, this fine suspension of liquid or solid particles in the gas, is mixed together with the oxidant and the fuel. And then it passes through here, and then it's the glass bead condenses anything which is not an aerosol, so we don't get like weird artifacts in the flame. Then the baffles, they sort of like well, will help to modulate the flow, so the flow is not too strong at times, too weak at times. It basically just make sure that there's a continuous flow, and then it'll pass up through here, and the force of the gases and things passing through here is what pulls the sample up. Usually you can have a pump, but usually it's not necessary. Just the force of everything flowing through the flame is usually sufficient. So then once these things are mixed together with the sample, it passes up through the flame, it goes through the burner head, and then there has been some ignition of the flame. And so we're burning the sample in the flame, along with obviously the oxidant and the fuel. So the premix burner is where the fuel, oxidant, and sample are premixed. So this is this part here, this tube. Then the nebulization, which happens here in the nebulizer, is the formation of small droplets. And then an aerosol is formed from a fine suspension of the liquid or solid particles, gas. In our case, it's a liquid, but you can form aerosols of solid particles. A nebulizer then creates an aerosol from the liquid sample, and the aerosol reaching the flame contains only about 5% of the initial sample. But that's okay, because so long as we've got a calibration curve and everything is properly accounted for, then we're going to get an okay result. So as I mentioned earlier, we can have different types of fuel sources, different flames. So the fuels are mixed with an oxidant, and then that produces different temperatures of flames. So common ones are acetylene gas mixed with air and acetylene gas mixed with oxygen, just because they're relatively low cost and they're pretty easy to keep safely. You can also mix acetylene with other things like nitrous oxide if you want an oxygen-free environment. Then hydrogen, you can mix it with air. It's quite explosive though, so it's quite dangerous. So it's usually acetylene, oxygen, acetylene, air really that we're dealing with here. Hydrogen, oxygen, and then cyanogen and oxygen gives us the highest temperature possible with these traditional AAS and atomic spectroscopy instruments. So the common one is acetylene air. Air is pretty cheap just to get compressed air. Mix it with acetylene. You can even just use an air compressor if you have one. And then here, acetylene oxygen is for refractory elements. These refractory elements are the ones that have high boiling points. Some compounds, some oxides just do not want to be separated into their ions. And so that's when we need these really high temperatures. So you can see that changing from air to oxygen gives us an increase in our temperature range by about 600 degrees. And it creates a much more consistent range of temperatures as well. So we talked about furnaces. So furnaces are really just really hot ovens. So here is a schematic of a furnace. So they're electrically heated graphite furnaces, and they offer greater sensitivity than flames. So that means that we can have them at more specific, more precise temperatures. You can see here on the previous slide the really broad temperature ranges for some of these things, more than 100, 200, 300 Kelvin. So it's really quite hard to keep a consistent temperature in the flame. And so one of the things that you can do is like you can change the ratio of the fuel to the oxidant, although it's still kind of a bit of a fudge. It's not really a perfect fix. So furnaces, because they're usually electrically heated by resistance, are easier to control the temperature of. They offer greater sensitivity than flames, and they require less samples. So maybe 1 to 100 microliters for furnace, sometimes 1-2 milliliters, maybe 30 milliliters for flames. You need a lot of sample for flame spectroscopy, atomic spectroscopy. So that's what I said back to the start, where I was talking about the idea that atomic spectroscopy of this sort typically utilizes large samples, especially the ones that use flames. So it's really just for bulk materials. It's not really suited for fine chemistry and like sort of pharmaceutical type applications. You need a furnace for that. So the furnace is kind of built like this. There's a picture of one. Here we have a schematic. So we have here the furnace part in the middle here. So we have where the light comes in and the light goes out. So that's where we're going to use to measure. We have this attached to some circuit, which is what we're going to heat with. Then we have the place where the sample will be placed, which is the curved Lavrov platform. It's the person who created this sort of setup. And then we have the furnace wall around here. So the light passes through this way. We can see an end-on view here. So this part is this part, and this part is this part, and then this is the furnace, and then this is the platform where the sample will be placed, and the sample can be placed through the top here, and then it can lie on it like that there. So when we're placing the droplets, what we want to do is we want to put the pipette in through the top, in through here, the sample port, and we want to push the pipette down as far as it goes without pushing too hard to the base of the furnace. And then we place the droplet out so that immediately it is coming into contact with the surface of the furnace. We do not want to pipette it like this, because if we pipette it like this, whenever we drop it out, the air pushing it out at the end will cause it to splatter, and we will get pieces of the droplet all over the furnace. So what we really need is the droplet to be in one uniform place. So this gives us bad placement, sample splatters, poor precision. Here we have good placement. All of the sample is kind of in the same area. And this is what we would do for a solid sample. So we just get it, place it in the middle, weighed onto the graphite platform like that. And so this is pretty accurate and highly precise placement of the solid onto the graphite platform. So inductively coupled plasma then, so this is what we talk about is reaching really, really high temperatures. You can see like even at the bottom of the flame, we have 10,000 Kelvin, plus or minus 10%. So it's pretty inaccurate. Again, like all of these flames, like the issue they have is that you can't really control them super well. And you can see that we have this flame. It's only really about 2 or 3 centimeters tall, where the sample aerosol is pushing through, but the temperature change from here is 10,000 Kelvin, here is 6,000 Kelvin. Now the temperatures are better here than they are in a flame, but they're still not perfect. They're more stable. Really can only be used for AES or mass spec. So that's why they're usually combined together. So AES is the emission, the broad spectrum atomic spectroscopy, where we can measure sort of all of the elements at once. And this is good for that because it's so high in temperature that it atomizes basically everything. And so it's really good for those refractory elements that don't want to burn or be atomized or whatever. Things like yttrium oxides and what have you. So here what we have is a Tesla coil, and it's going to ionize the argon gas that we're pumping through. And so this free electron is then accelerated and oscillated in the RF induction coil, which is passing around here. And then the accelerated free electrons collide with the argon atom and transfer energy so that we have Joule heating, which is IR squared. So that's just the equation for the Joule heating. Here we have a schematic of the part down at the bottom here below the flame. So this is the 2-turn radio frequency load coil. So this is what is accelerating the free electron and oscillating it. So this blue part here is this part here. Then the flame comes out here, and then we have the 2 detectors. So we have detector position here for axial viewing. We have detector positioning here, or for lateral viewing here at the side, and axial viewing. So if the flame's coming out like this, for viewing down into the flame. Now this detector is going to be okay because the flame won't actually reach that high. I mean, it'll be really hot, but it won't really damage the detector so long as it's far enough away. Then inside here we have the sample aerosol inlet. It's kind of pulled through in the same way as the flames. They're all kind of nebulized and mixed here just before the radio frequency load coil. The plasma gas comes in through here. The coolant gas comes in through here, so we don't reach too high a temperature and destroy the whole thing. Sample tube is this one. Then we have the plasma tube. Then we have the coolant. All passes up through here. And then gets ejected into the radio frequency load coil, which turns around twice and really accelerates the free electrons, which collide with the argon atoms and transfer energy. And we get this really, really intense heating, which produces these very high temperature flames. So the flame effect, the flame temperature effect on AAS. So the temperature is key and is critical in determining the degree to which a sample breaks down. So the atomization efficiency. So how many atoms are in the ground excited or ionized states are the population. So the Boltzmann distribution kind of describes how these are distributed between the ground and excited states. So this describes the relative populations of different states at thermal equilibrium, and the relative population of any two states is given as so. So the population here is going to be the population of in the excited state versus the population in the lower state, which is equal to the degeneracy of the states. So the degeneracy is how many of orbitals have that same, or how many states have that same energy. So this would be the lower energy state. This is the higher energy state. And that's going to be e to the minus delta E KT, where this is the Boltzmann factor here, this KT. So here's like an example of the degeneracy. So at the ground state, the degeneracy is 2 because there are 2 states with the same energy. And then the excited states, there are 3 states with the same energy, or 3 levels with the same energy. So let's have a look at some calculations then for the Boltzmann distributions. So we're looking to find the population on the excited state, the effective temperature on the excited state population. So if you have a sodium atom at 2600 degrees Kelvin in acetylene air flame, then we use this equation here where the population of the excited state over the population in the ground state is equal to the degeneracy of the excited state versus the degeneracy of the ground state, or well, really any lower energy state. Then we have this term here, which is the Boltzmann term. So delta E is going to be the change in energy. So that's going to be 3.371 times 10 to the minus 19 joules per atom. The degeneracy of the ground state in this instance is 1, and the excited state is 2. So then we fill in the numbers into our equation. So we have here the population ratio between the ground and the excited state. We have here the degeneracy. We have here the Boltzmann, or the delta E. We have the Boltzmann factor here, K. And then T is temperature, so that's 2600, which we were asked. Then we find out that this ratio is 1.67 times 10 to the minus 4. And then we're asked what happens if we increase the temperature to 2700 degrees Kelvin. So we find out that, so this number is really small. That indicates that most of the electrons are actually in the ground state. So what if we increase the temperature to 2700? What's going to happen? Well, what we see is an increase. The only thing that's changed here is the temperature, now 2700 versus 2600. So it's going to be equal to 2.37 times 10 to the minus 4. Still really small, still indicating that most of the electrons are in the ground state. So we find out how much of an increase in the excited state population there is based on a 100-degree change in the temperature. So we have here 2.73 minus 1.64. We omitted the times 10 to the minus 4 since they're both the same. Divided by 1.67 times 100% is equal to, or approximately 42% increase in the excited state population. So you can see, hopefully you can see now why it's so important to make sure that the temperature remains static. Because if it doesn't, then we suddenly start to change the population. So you need to do your calibrations and your actual measurements at exactly the same temperature, or because of the Boltzmann, you're going to, the effect on temperature in the excited state population, or like the Boltzmann distribution, is going to change. And so you're going to end up with a more intense light at a higher temperature. So sodium, so yeah, very few are actually in the ground, or in the excited state. Almost all of the atoms are in the ground state. And then 100 Kelvin rise in temperature there's no noticeable change in the ground state population. So it's okay for atomic absorption. But if we're doing emission, then suddenly we have this massive increase in the excited state population. So in atomic emission spectroscopy, the flame temperature must be kept stable. But for atomic absorption, it's really not that important. For ICP, the high temperature means there is high sensitivity, and a stable plasma temperature means very reproducible data, which is why for AES measurements, it's really moving towards using ICP as opposed to the flame. So with regards to instrumentation, some things we have to consider. Next session, we'll talk about the actual components in an AAS in more detail, especially the light sources and things like that. But for now, we'll just talk about some of the things that we have to consider. So in atomic spectroscopy, absorption and emission lines are very sharp. So we have 3 sources of broadening. We have the uncertainty effect, which is around about 10 to the minus 4 nanometers, which broadens. Doppler broadening around about 10 to the minus 2, 10 to the minus 3 nanometers. Pressure effect, the collisional broadening of around about 10 to the minus 2, 10 to the minus 3 nanometers. And so what are these? So uncertainty broadening is the natural line width. So this is from the Heisenberg uncertainty principle. And so the shorter the lifetime of the excited state, the more uncertain its energy is going to be. And so it can be described by this, where delta E times delta T is going to be greater than or approximately greater than H over 4 pi. So delta E is the uncertainty in the energy difference between the ground and the excited states. And delta T is the lifetime of the excited state before it decays to the ground state. So around nanoseconds in atomic spectroscopy. And H is, of course, the Planck's constant, and pi is just the pi number. Atomic line widths, then Doppler broadening. What is Doppler broadening? It's really dependent on the observer position with regards to the sample and the direction that it's traveling. So for example, atoms in the hot flame have atomic motions in every direction. They're moving towards the detector, they're moving away from the detector, they're moving in untold number of directions. So the Doppler line width broadening can be described as here. So the change in the wavelength is approximately equal to the wavelength times 7 times 10 to the minus 7, which is a constant, times the square root of the temperature over the atomic mass. So changes like for sodium, it's 23, for iron, it's 56. We'll see an example calculation on the next slide. So here are a couple of Doppler broadening cases. So here we have a light source, which is passing this way towards an observer or a detector. And so the sample is moving towards that photodetector. So if the motion is towards the photon detector and away from the photon source, which would be this one, actually, the light source is here and it's traveling in this direction. So this is moving away from the photon source. It's moving towards the photon detector, then the radiation wavelength emitted or absorbed decreases. And so this is high frequency. If the motion is receding from the photon detector and towards the photon source, so in this case, it's moving towards the light source and away from where the detector would be, then the radiation wavelength emitted or absorbed increases. And this means that we have a lower frequency, which is observed. So depending on that, Doppler broadening tries to take into account both instances. So Doppler broadening then, so heavier atoms tend to have less Doppler broadening than lighter atoms. Atomic line widths, the broadening then, so here's a sample calculation. So we're asked atoms in the hot flame, atomic motions are in every direction. So we have Doppler broadening. So for emission from iron, which has a mass of 56, we're near the wavelength of 300 nanometers. So that's what we're going to use. From iron at 250 Kelvin. So we can see here the numbers have all been color coded for easy checking. So delta lambda, this is the Doppler broadening, is approximately equal to lambda times this constant 7 times 10 to the minus 7 times the square root of T over M, where T is the temperature and M is the mass of the element. So that's going to be equal to 300 times the constant, 7 times 10 to the minus 7, times the square root of 2500 over 56, which is equal to a broadening of 0.014 nanometers, which doesn't seem like very much. But whenever we consider how narrow these lines actually are, it is reasonably large. And so this is an order of magnitude larger than the natural line width. So it has a big effect. It doesn't seem like it does. It seems really small. But because of the line-like nature of these peaks, it's a significant broadening. Then pressure broadening, so this is caused by atoms interacting with other atoms. It's analogous, but not the same as the sort of concentration problems that we have with the Beer-Lambert law and liquid samples in molecular spectroscopy like UV-Vis. So collisions of the absorbing or emitting atoms with other atoms or ions in the heating medium. So this tends to shorten the lifetime of the excited state because what it does is it provides an alternative pathway for that energy release. The energy is released by the collision. And so this causes a change in the energy level of the ground or excited state, and it causes line broadening. So what happens here is the high pressure causes higher collisional frequency, means there's greater line broadening. So the higher pressure means that they're either closer together or they're moving faster. And so they hit each other more often, which means that they kind of relax quicker. So the basic principle of AAS, then, atomic absorption spectroscopy, is an analytical technique for measuring the concentration of elements, and it uses the absorption of light to determine concentration. So it's not really affected by flame temperature, which is why using flame temperature for AAS is still fine. Like you've got very minimal changes in ground state population based on temperature. or based on small fluctuation of temperature around 100, 200 degrees. It's not a big deal. AAS quantifies the absorption of ground state atoms in the gaseous state, and these atoms absorb UV or visible light and are excited to higher electronic energy levels. And this absorption of that light, so it's the removal of those wavelengths from the light which passes through the flame and is then picked up by the detector. It's the difference between the incident light and the light after absorption, which is what we're measuring. And then the concentration of the analyte, the atom, is determined by the amount of absorption. Concentration is determined then using a calibration curve, and then after instrument calibration with standard solutions, or by the standard addition method. So we learned about those back in module 1, the standard addition method, instrument calibrations, that was our linear regression, our calibration curve. We would measure out standard solutions, and that's only really possible for simple cases. If we're like dealing with environmental samples, like we want to know how much copper there is in a particular river, or we want to know how much pollution is being caused by a local port or something like that, or nearby an airport or something like that, then what we need to do is use the standard addition method by spiking our environmental sample with some extra analyte, because the matrix effect can cause aberrations in our data. Then AAS is commonly used for the detection of metals and metalloids in environmental samples. So it's really, really good for that. It's basically built for those things. And so here are some of the detectable elements for AAS. The ones in purple are all the ones which are detectable. The ones in cyan, not so much. So these are all AAS detectable elements. We have things like most of the metals can do this, except technetium, osmium, hafnium, lanthanum, and so on. But things that are typical environmental pollutants like iron, copper, platinum, palladium, lead over here, common pollutants that need to be kept on top of, need to be measured, need to be cataloged, and so that we don't end up with poisoned or polluted natural resources. So you can see that the vast majority of the periodic table is accessible to us whenever we're making our AAS measurements. So this sort of brings us towards the end of this introduction to atomic spectroscopy, and especially to atomic absorption spectroscopy. Next time, we'll talk in more detail about some of the parts of the instrument that make it useful for these measurements. And today, we've talked about, obviously, the spectrum, especially the emission spectrum, how different types of broadening can really affect the measurement, how certain things like temperature changes are bigger problems for emission spectroscopy rather than absorption spectroscopy. That's like the Boltzmann distribution, pretty heavy on physics, but really it's the cause of that problem in emission spectroscopy. So it is something that you really need to be aware of. So before we end, let's go through our comprehension check. And so we're asked, as always, I'll read out the question, then I'll give you a handful of seconds, try to do it yourself, and then we'll go through the answer together. So we're asked, what is the Doppler broadening at around about 200 nanometers for a sodium line at both 210 degrees Kelvin and 230 degrees Kelvin? And please pause for more time, try to answer the question, and then we'll go through it together. Okay, pause for more time if you need it. Right, here comes the answer. Okay, so for sodium at 200 nanometers, we have a mass of 23. We have our temperature at 210 Kelvin. We have then the Doppler broadening, which is delta lambda is equal to lambda times that constant, 7 times 10 to the minus 7, times the square root of the temperature over the mass. So that's just our equation. It's the same in both instances. Then for the most part, the stuff is all set up the same. So it's 200 nanometers, the constant. The only thing that's changing is the temperature here over the mass. And so what we find is that the higher temperature, we have more broadening. We have 0.0013 nanometers broadening for 210 degrees Kelvin. And then for 230 degrees Kelvin, we have more broadening, 0.0014 nanometers broadening. So it is kind of, it doesn't seem like very much, but actually it is whenever you consider these are line spectra, basically just points. There is an issue then with emission spectroscopy where you might have a lot of lines overlapping with each other because you have a lot of different elements. This could make it difficult to find the elements if you're too high a temperature, because what can end up happening is you get too much broadening. Although if it's really heavy element, the Doppler broadening has less of an effect. And why is that? Well, because this mass gets larger, so this overall number gets smaller. So that makes everything else smaller. Okay, thank you for checking out this session. Let's meet again next time.